Hi everyone, in this video, we're going to start talking about how to handle outliers. Outliers are data points in a dataset that don't match the overall distribution. They deviate significantly from the general pattern, and they're often caused by things like measurement errors, data entry mistakes, or rare events. In our earlier discussion, we came across an example where a restaurant had 6 guests, but they only ordered 1 Coke. Clearly, this is an unusual order because typically 6 guests would order around 6 items. After cross-checking with the rest of the dataset, we can assume that only ordering 1 Coke isn't a data entry error. Of course, it's possible that the number of guests was recorded incorrectly, but for this example, we'll assume the data is accurate. That makes this data point an outlier. Outliers can have a big impact on statistical analyses and machine learning models, so it's really important to handle them properly. Let's use this regression task as an example to analyze the downsides of outliers once again. In this example, we're trying to uncover the overall pattern in the dataset. In other words, we want to find a curve that ideally covers all the data points and represents the underlying distribution of the dataset. The green curve in the graph is an example of a converged model. Although it doesn't connect every data point, it still captures the overall trend of the data distribution, so we consider it a converged model. Once we have this trained model, we can use it to make predictions for the future. Since it's a continuous curve, we just input a future date, and the green curve will provide a corresponding stock price, which is the model's prediction. Now, let's make a few simple modifications to the dataset by adding some outliers. We can see that outliers are data points that clearly deviate from the overall distribution, and they only make the model's training more difficult rather than beneficial. Suppose we train a model that perfectly connects all the outliers, like the new green curve in the figure. This means the model is not only learning the overall pattern of the original dataset but is also being misled by the noise from the outliers, and ends up learning some unnecessary patterns. Compared to the expected trained model on the left, the model on the right becomes too volatile due to the noise. When we use this model for predictions, the excessive fluctuations lead to unstable results, which in turn reduces the prediction accuracy. I want you to understand why we should detect and fix outliers by comparing these two graphs. If we remove the outliers, we reduce the noise in the dataset, which speeds up the training process. This means we can get a curve that accurately reflects the overall trend of the dataset in less time. Moreover, by mitigating noise, our trained model will make more stable predictions in the future, thus improving its robustness. Maintaining data quality is always something we need to care about. Outliers, like missing values, are issues that should be relatively easy to detect. So whenever we have a dataset, we should always start by checking for outliers. If the outliers are caused by human errors, such as incorrect data entry, we can try using data imputation to fix the data. But if the outliers are difficult to correct, we should simply delete those data points. However, if we end up deleting too many data points, we need to recheck the data's distribution to make sure we don't introduce bias. If that happens, the only solution might be to collect more data to enrich the dataset. One thing to note is that outliers aren't always a bad thing. In some specific applications, we actually appreciate outliers because they can contain important information. Take a moment to think, in what kinds of applications would we really care about outliers? 1, 2, 3, 4, 5? In cases like fraud detection or rare disease prediction, outliers can be extremely valuable. In these applications, it's often the outliers that provide the crucial information we need. The focus of our model training is to learn the patterns associated with these rare events rather than just the overall trend. If you remove outliers during preprocessing, you risk giving the model a dataset that lacks the very anomalies it needs to recognize, such as fraud. That's why it's important to combine domain knowledge with a deep understanding of the task when preprocessing data, instead of simply relying on a fixed, one-size-fits-all approach. Now, let's look at some common techniques for detecting and addressing outliers. We can generally divide these techniques into 3 categories: mathematical and statistical solutions, model-based solutions, and data visualization. In this topic, we'll focus primarily on statistical methods, especially the z-score and interquartile range methods. As for model-based solutions, you need to consider whether they're really worth using. The purpose of data preprocessing is to prepare data for a machine learning task, and training specialized models just for preprocessing can sometimes cost more than the benefit you get. So if you're thinking about model-based solutions, make sure to weigh whether they're truly necessary or if there's a simpler, more cost-effective alternative. Lastly, there's data visualization. This is a very common practice when you get a dataset. You can start by writing some code to plot a scatter plot to check out its distribution. If there are any data points that clearly don't belong, you can often spot them just by looking. Then, using your domain knowledge, you can quickly analyze whether those points are outliers for your task and decide whether to remove them. But in practice, we might encounter situations where it's hard to tell. We might intuitively think some data points are outliers, but there isn't solid evidence to back that up. For instance, in this one-dimensional dataset, the value 100 doesn't quite fit with the other four data points. It might be an outlier, but we don't have a strong reason to be sure. In these cases, we need to use statistical methods to define what an outlier is and then determine whether 100 meets that definition. If it does, we fix or remove it. If it doesn't, we keep the data point. First, let's look at the z-score method. The z-score is a concept from statistics that tells us how far a data point deviates from the mean of a dataset, measured in terms of standard deviations. The formula for the z-score is shown on the slides. In this formula, x is the data point, the mean is the average value for the feature that x belongs to, and the standard deviation is the standard deviation of that feature. The z-score indicates the relative position of a data point within the distribution. Specifically, when the z-score is greater than 0, it means the data point is above the mean. If the z-score is 0, the data point is exactly at the mean, and if the z-score is less than 0, the data point falls below the mean. Let's go back to this example to see if 100 is an outlier. We can easily calculate that the average value in the dataset is 30, and the standard deviation is roughly 35. Remember, the standard deviation is the square root of the variance. We've discussed how to calculate variance before, so make sure you're comfortable with those formulas. When you have a small dataset, you should be able to manually compute the standard deviation and average value, and then use them to calculate the z-score. This type of question might come up on the exam. Returning to our example, using the z-score formula, we calculate the z-score for each data point, which gives us a new set of values. Based on the definition of the z-score, do you have any intuition about whether 100 is an outlier? If you've studied probability theory or the normal distribution, take a moment to think about the physical meaning behind each data point's z-score. Again, the z-score represents the relative position of a data point in the distribution, with the center of a Gaussian distribution being the average value. In this case, mu is the average and sigma is the standard deviation. So, if a data point is exactly one standard deviation away from the average, its z-score will be 1, and if it's 2 standard deviations away, the z-score will be 2. In a normal distribution, we know that any given data point has about a 99.5% chance of falling within 3 standard deviations of the mean. If we set the mean to 0, then the x-coordinate of a data point directly corresponds to its z-score. Because a 99.5% probability is extremely high, we can define the remaining 0.5% of cases as outliers. When a data point has a z-score less than -3, it means it is below the average and far from it. Similarly, if a data point's z-score is greater than 3, it means that the data point is above the average and still far from it, occurring only with a very low probability. Therefore, if the absolute value of a data point's z-score exceeds 3, we consider that data point an outlier. Through this discussion, I hope you realize that using z-scores to identify outliers is a very statistical approach. We're simply defining cases that have an extremely low probability of occurring as outliers, not necessarily saying that these data points don't exist or are mistakes. Z-score is a common way to define outliers, but it does have some drawbacks. First, when we use z-score, we assume that the dataset follows a Gaussian distribution. However, not every practical dataset fits this pattern. If the dataset's distribution doesn't match a Gaussian, then relying on this assumption can lead to incorrect results. In this example, we only have 9 data points. If we plot a probability distribution using just these 9 points, you'll see a series of discrete black dots. Even if we connect them, we'll only get a straight line instead of the expected red Gaussian distribution. In other words, this dataset doesn't match our assumption of a Gaussian distribution. However, the underlying meaning of the dataset should still hold true. For instance, in a classroom, the distribution of students' grades is generally normal. Students who work hard tend to score higher, but the number of high-scoring students is usually similar to the number of students who don't put in much effort. This means most students' grades cluster around the average, with only a few scoring very high or very low. So, why doesn't this dataset's distribution match a normal distribution? The reason is that there are too few data points to accurately represent a normal distribution. This is another drawback of using z-scores. They are very sensitive to the size of the dataset. Additionally, when using z-scores, we can adjust the threshold based on our understanding of the task and our domain knowledge. For example, we typically set the threshold at an absolute value of 3, but you might choose a threshold of 1 instead. A threshold of 1 would require non-outliers to be very close to the average. This introduces some subjectivity, since different people might interpret the same dataset in different ways. That's another disadvantage of relying solely on z-scores. Finally, let's look at the interquartile range method. This is another technique based on mathematical and statistical analysis. We define the 25th percentile of the dataset as the lower quartile and the 75th percentile as the upper quartile. By calculating the difference between these two values, we can determine the range that covers the middle 50% of the data points in the dataset. Then, we define a threshold, say, 1.5, and calculate an upper and lower bound. Any data point that falls outside these bounds is considered an outlier. Let's take another look at this example and determine whether 100 is an outlier. After doing the calculations, we find that the upper bound is around 27. Clearly, 100 is well above 27, so 100 is considered an outlier. In this dataset, it's the only outlier we have. However, in our previous analysis using the z-score with the default threshold of 3, 100 wasn't considered an outlier. This comparison should help you understand that whether a data point is classified as an outlier isn't absolute. It really depends on the method we use and how we define an outlier. Finally, let's briefly go over what we should do after detecting outliers. There are 3 common approaches. The first is the most straightforward. Simply delete the data points that are outliers. However, remember that we should maintain the integrity of the dataset as much as possible, so we shouldn't delete data points without good reason. The second approach is to find a suitable value to replace the outliers. For example, we can use data imputation to generate a rational candidate value. The third approach is to analyze the specific machine learning application. If the task depends on outliers, for instance, in fraud detection we might not want to treat them as errors at all. In cases where we need to detect anomalies, these tasks are called anomaly detection, and if applicable, we'll cover that topic in more detail in the future. That wraps up our discussion on outliers.